Thank you, everybody. So my name is Juan Luis Cano, and we're going to talk a little bit about dataframe libraries in Python with particular attention to polars, which has become my favorite Python library in recent years. So first of all, I'm going to do a bit of an introduction, and we're going to talk about pandas, which is the library we all know and love. What are happening there, its success, and also especially what are the current limitations. I'm going to gloss over some of the alternatives that exist today, and then I'm going to do a little bit of a live demo to showcase some of the capabilities of polars. So first of all, a few words about myself. So I'm an aerospace engineer on a mission to accelerate the solidarity economy through technology. I'm currently working as a data scientist advocate at Orchest, which is a company creating an open source pipeline orchestrator. And I've been involved with the Python community in Spain for the last 10 years or so. I created the Python Spain nonprofit. I organized the first 7 editions of PyCon Spain, a few years of the Python Madrid meetups, and at the moment I'm organizing the PyData Madrid meetups. So if you're ever in the capital of Spain and want to uh, give a talk or just attend our meetups, you are more than welcome to do so. So feel free to reach out to me on LinkedIn and follow me on GitHub. And yeah, that's it. So a little bit of context of why we're giving this talk. So at Orchis, we want to empower data scientists and data engineers by developing a pipeline orchestrator that is powerful but also easy to use. And we're noticing that the extract and load phases of data processing are increasingly being commoditized, but the transform is still highly customized to each use case and potentially very complex. So we set ourselves to answer the question, are our users using the best tools available? So we started doing a little bit of research on what was out there beyond the current tools that most of the people are using, with a focus on data frame libraries first. And we cannot speak about data frame libraries with Python if we don't mention pandas, right? So this plot here that became quite famous 5 years ago comes from Stack Overflow blog post that describes the rise of Python in the age of data science. And basically, if you break down each of the tags that the Stack Overflow questions had, you could see that even though Django and Flask have been slowly increasing over the years, it has been the PyData stack and fundamentally NumPy, Matplotlib, but very especially pandas that brought Python to the position it is today. So they have been key to the success, and we could safely say that 80% or 90% of data scientists out there use pandas or some of the other Python libraries. However, pandas was designed some years ago with some assumptions in mind that do no longer hold, and made some decisions in the design that are no longer optimal. So there's this blog post by Wes McKinney, the creator of pandas, called Apache Arrow and the 10 Things I Hate About Pandas, that I highly recommend you to read, and goes over some of these limitations. So basically, the summary goes a little bit like this. So many pandas operations don't really take advantage of multi-core machines or smart query planning on things like that because of how the library is designed. So you know that when you're performing a chain of operations in pandas, each of these intermediate results needs to exist in memory for the next operations to happen, and therefore this can incur in some inefficiencies because most likely pandas is computing things that we will no longer need down the line. Then there have been some efforts to try to rewrite some parts of pandas so that the GIL could be released or some parts could be parallelized, and there has been mixed success. So some things can be indeed um, successful to being parallelized, but some others haven't. I'm seeing in the comments that the sound is a little bit quiet. Not sure if that's still the case, but I will try to compensate for that. Hopefully that's a little bit better now. Otherwise, let me know. And apart from that, Pandas has some lousy memory management technique with some things. So for example, the way missing data is handled in Pandas is a little bit limiting. There's essentially two ways. So one is declaring a sentinel value like none or none or not a time, not a date, etc. to signal that there's a missing value there for whatever reason. This is more memory efficient because you don't need to essentially duplicate the data. But the downside is that the CPU cannot be as efficient going through that data. And then there's another strategy, which is having a Boolean mask that essentially tells the library whether a specific value is valid or not. And in recent years, especially after Arrow was created, this second strategy has been favored much more strongly. Then Pandas has no native capability of doing memory mapping, and also the way strings and categories are stored internally are a little bit inefficient. So these are not huge problems for the average practitioner, but when people want to apply Pandas in production for large quantities of data, then this starts becoming a problem. So what are the alternatives then? So I started navigating the landscape of current alternatives in Pandas, to Pandas, and it was kind of confusing at the beginning. I was not exactly sure what each of these alternatives were doing. So inspired by the famous quadrants by Gardner, I created the dataframes charming quadrangle with some of these alternatives mapped. So on the lower left corner, you have the things that are most similar to pandas that are applicable for datasets that are small or medium in size. And apart from pandas itself, you have Rapids. So Rapids is a project that brings pandas and other libraries to the GPU. So if you have a dataset that is manageable by your local computer, but you want to accelerate its processing, then you might be interested in trying out Rapids if you have a GPU to use it. Then on the upper left corner, we have libraries that try to imitate the Pandas API to allow a simple transition from one to the other, but they bring it to a distributed setting. So essentially, you are able to process much, much larger quantities of data, more or less with the same API. The most famous of these ones is Dask, that has been around for many years already. And what it does is chunking the data into smaller pandas data frames and then scheduling all of that very efficiently. And then Modin uses Dask under the hood and tries to make even a more seamless transition from pandas to a distributed setting. On the upper right corner, I called it the recovering Hadoopers. There has been Apache Spark all this time and PySpark. And the reality is that for some reason, the evolution of Apache Spark and PySpark has been kind of in parallel to the rest of the PyData community, and there hasn't been much intersection. But nowadays, they are converging more and more. For example, now Spark ships Koalas, which is a Pandas compatibility layer. So it's easier than ever to use Pandas-like API on Spark. However, there are many people that don't like Spark for whatever reason. And so we have on the lower right corner some other libraries that don't try to imitate the Pandas API, therefore they don't offer an easy transition path between the two, but they offer some very interesting things that are worth exploring. So the first of those is Apache Arrow. Apache Arrow is not a data frame library per se, in the sense that it doesn't have a high-level API that you can use, but it's the foundation for many other libraries that have been created in recent years. So Arrow is it defines itself as a language-independent columnar memory format that is designed for transient data, so not necessarily for storing data to disk. To store data to disk, we have Apache Parquet and the feeder formats. And it allows you to use it from many different languages. So the PyArrow bindings use the C++ ones under the hood, and then there's a native Rust implementation, and there's many other bindings in different languages for Arrow. And on top of Arrow, there's Polars. So Polars markets itself as a lightning fast dataframe library for Rust and Python. Is for in-memory data frames, even though they have added streaming capabilities very recently, so they can process datasets that are larger than RAM now, doing out-of-core processing. The most interesting thing about Polars, and we're going to see that in a moment, is its expression system. So you have a series of very functional APIs that you can apply to the Polars data frames, and they are very elegant and very efficient. And Polars is able to optimize this series of expressions, building a query plan very similar to what traditional SQL databases have done for many, many years. And even though the project is very young, it was created in the middle of the COVID-19 pandemic in May 2020, if I'm not mistaken. The project is really promising, and I've been using it more and more recently. There are other projects that also belong to this category. So if you want to know a little bit more about Arrow, I have a previous talk called The Great Python Data Frame Showdown that I gave at PyData London 2022. You have the recording online. There's also DACDB, which is not really a data frame library. It's more of a in-memory SQL library that you can use to transfer data between DACDB and Polars back and forth. You can check out a blog post that I wrote on the matter. You also have Fugue, which is a unified interface for distributed computing. It has several backends, for example, Spark, Dask, Ray, and so forth. And there's also IBIS that tries to provide a unified interface, a SQL-like interface in Python, again with several different backends. So without further ado, if there are no further questions, let's do some demo time. So I have here some data pipelines that I'm going to use. So I'm going to download the Stack Overflow sample from Kaggle. And this Stack Overflow sample contains roughly 1% of all Stack Overflow questions and answers along with its tags. So we're going to process all of that. And I'm going to run through a notebook that I already have that covers some of the most interesting concepts of Polars. So first of all, you can see that I'm going to restart the kernel just in case. So you can see that I'm using the latest version of Polars, 0.15.1 at the time of recording this talk, which was released less than a week ago. And we have a couple of CSV files here. So we have 1.8 gigabytes of questions and 63 megabytes of tags. And we're going to see if we can answer the questions of what are the most popular Python questions in general and do some exploratory data analysis here. So Polars has a readCSV function, very similar to the pandas readCSV that we're used to use. And this returns a Polars data frame, as you can see here, with a few columns and many, many rows. You can see that the length of the data frame is 1,264 something thousand rows, and then the tags is roughly 3 times that because most of the questions have more than one tag. We can check what are the D types of this data frame. So we see that we have a few integer columns and also some text or categorical variables, and also that Polars allocated 1.8 gigabytes more or less of RAM to read this data in memory at the moment. They're asking to increase the font size, so there we go. Hopefully that's a little bit better. Let me know otherwise. And we can use some methods that we're used to from pandas as well. So, for example, we have head to display some of the first lines. By the way, if you do a print of a Polars data frame, it has this nice is ASCII representation that is quite useful for copy pasting and stuff like that. We also have describe that gives a statistical summary of the data. And then we can do things, okay, give me the value counts of the tags, and then sort by count and give me the most popular ones. So you can see that in this data set, the most popular tags are JavaScript, Java, and C Sharp, and we have Python over here. Okay, but this is very similar to what we've done with pandas traditionally. So what are the interesting things of Polars? So Polars has this concept of expressions. So as you can see, I'm declaring here a column called score and then applying the median of that. But this .call thing comes from Polars directly. There's no data frame involved here, which means that this expression is independent from any data frame where it's applied to, right? And then if I pass that expression to some of the Polars contexts, for example, select, then it's going to compute the result of that expression for this particular data frame. And this is very powerful because it means that you can decouple the data from the computations that you want to express on it. If you happen to pass more than one expression like this, then you can compute several things at one. For example, you can compute how many unique IDs are there in this data set and give it the name num unique users. You can compute what's the mean score globally and call it mean score. You can see what's the maximum length of the title and then call that max title length. Or you can see what's the maximum length of all the text columns, which is super interesting, and then calling it with a suffix max length that will be applied to each of the UTF-8 columns. And the interesting thing is that Polars is going to apply all these expressions in parallel because they are completely independent from each other. So you don't need to wait for one to finish to start doing the other one. And this is going to be as efficient as it gets. The other interesting thing about Polars is that apart from the str methods, I don't know if any of you has been working with pandas data frames that have a column of lists. For me personally, it's a little bit annoying when this happens because one needs to use the .str methods also for this kind of series of lists, which I find a little bit unintuitive. And the thing is that Polars has a dedicated namespace for this, which is .r, and you can apply several methods to that are going to be specific for columns of lists. Okay, so far so good. Interesting API, but then what happens when we have very large data? So imagine that I now want to join my data frame of questions with the data frame of tags, right? If you try to do that in this machine, it's not particularly powerful. So I have a few gigabytes of RAM only. And doing this join operation is going to crash my machine. So I'm not even going to try to do that. But what you can try instead is to use the lazy capabilities of Polars. And the idea is that by calling an .lazy method after from an in-memory data frame, then that's going to allow you to chain a series of methods that will not execute themselves, and instead they will accumulate in a query plan that then you call with .collect, and that performs the result. So essentially I'm doing here a join between the TF and the tags, also with the lazy interface. On the ID, I'm doing a semi-join, which is a magical join I discovered with Polars that is like an inner join but discards the extra columns. And then I'm filtering where the tag, the lowercase tag contains the string Python, right? So I'm essentially now having a data frame that contains both the questions and the tags themselves, and I'm able to filter that. Um, all right. Now I set myself a reminder to not load both things at the same time to continue. And I'm going to wrap up because I want to leave some time for questions. So you see, before, to use the lazy interface, I use the .lazy method on an in-memory data frame. But what I can do instead is to use a scan CSV rather than a read CSV that directly returns a lazy data frame. So this is not going to load the whole data frame in memory, and instead it's going to scan it so that I can make a more complex query potentially without clogging my computer RAM. So I'm now repeating the same join that I did before, but now I'm sorting all the questions by score descending, and I'm limiting that to the first 1,000 ones. And the interesting thing is that I'm storing that in a variable called plan, and then the result of the plan would be plan.collect. But you can go and visualize this query plan here with this graph visualization, where you can see that there's on one side this CSV scan, and then there's another table coming from another side. It's doing a semi-join, some filtering, and so forth. So Polars is able to devise this query plan very similar to what Dask does at another level. But it's also going to optimize the operations a little bit. So I'm going to gloss over the rest a little bit more quickly. So you can also do list operations really easily. For example, like group by ID and then creating a list of tags for every ID, which is very convenient. You can see if any of the tags contains the substring Python, because potentially they could be like Python 3 or Python dash something else. And you can do many other things. So the whole material is online. I'm going to share the link with you in a moment. So we're going to close the demo time for now, and I'm going to head back to some quick conclusions. So first of all, what about the index? Nowhere in all the code that I showed, we talked about an index, and we're used in pandas to have that, and for it to be a very central part of all the processing we do. And in fact, there's very opposed views about that. So from the Polar documentations, they say that indexes are not needed, and not having them makes things easier, convinces otherwise. So a pretty hard stance against indexes, or at least not in a sense that they're completely required, right? But then there are some other people like James Powell, very famous in the PyData community, that says that basically all the pandas operations are framed as a transformation on the index and that it's an essential cornerstone. What about Dask then? We all saw that this is for a single machine, but you might be wondering what happens if I want to go for a distributed setting, but using polars, right? So it turns out that Matthew Rockling and Richie Vink, so the creators of Dask and polars respectively, have been working on a prototype recently. This was a screenshot taken 1 month ago. And they're waiting for feedback. So if you want to let them know what exactly do you expect from a distributed polars library, let them know. Chime in and participate in the conversation. So some conclusions: pandas has some limitations and inconsistencies. By imitating the pandas API, you're necessarily bound to reproduce some of those inconsistencies. And Polars is an excellent project that departs from the pandas API, but nonetheless provides some very interesting capabilities. And I bet that in the very near future, there's going to be a distributed solution based on Polars that's going to be awesome. So thank you very much. A special thanks to Kevin Coe, James Powell, Cameron Riddell, Richie Vink for giving some early feedback on this talk, inspiration, discussion. You can follow me there. I will share all the materials online, and I'll be happy to take any questions. Thank you very much.
All right. Thanks for the presentation. I think we got a lot of questions from the YouTube channel. The first one is asking, would there be a address where they can be finding the demo notebooks?
Yes, so the demo notebooks are on my GitHub. So if you go to github.com slash astrojuanlu tag polars, you will find them. I'm not sure I can share that right now on YouTube because sharing links is a little bit restricted there. But anyway, if you chime in on Discord or just go to the description of the talk online, you will see all these notebooks and you can import them and do whatever you want.
Cool. And another question we got is, would it be possible for us to convert Polar DFS to pandas?
Yes, indeed. So, for example, if you have these tags data frame here that I have, there's a two pandas method, if I'm not mistaken. There we go. And then you see this returns a pandas data frame directly. So, yeah, the conversion is really easy.
Gotcha. And we have another question. I think last question would be, how does lazy query work with limited memory?
So how does the lazy query work with limited memory? So the idea is depending on the engine that you use, there's the conventional engine that was there at the beginning of Polars that still needs all the intermediate results to fit into memory. But nonetheless, it tries to be as efficient as possible and avoid loading results that are not going to be needed. Then there's a streaming engine that you can try. So if you do .collect streaming equals true, then this is not optimized for speed, but optimized for throughput instead. And sorry, not for throughput. I mean for out of core processing. And you should be able to process much larger data sets with that. This is quite new from the recent versions.
Cool. And I think we'll be picking our one last question asked by Daniel. Is there any way to easily convert from prototype to pandas data frame or the opposite?
Yeah, for pandas, for polars to pandas, we already did that. To do the opposite, we have, I think it's build data frame from, no, I think, yeah, it's from pandas. And you can
There you
pass
go.
here pandas data frame. So essentially you could do something like this. I'm not sure if I have enough RAM to do this. Yeah, I do.
Cool. All right, I think that will be all time we're having here for today. I could still see there are a lot of questions asked on YouTube channel. Guess we can proceed to the Discord later on. Again, thank you Juan for coming to the PyData Global, and thanks everyone for joining us today.
Thank you. Thank you very much. See you all.